Earth provides us with many things: running water and food for survival, an atmosphere that helps protect us and gives us air to breathe, a magnetosphere that protects even that atmosphere from being stripped away by cosmic radiation. It is partly because of these things that we are here today at all, to be capable of studying our universe and the many wondrous things found in it. When it comes to observing our universe, though, many of these things that protect us at the same time get in the way. Let's take the air, for example. It both distorts light coming through it and also outright blocks some of the wavelengths of light from reaching us at all. Have you looked up at the sky before and noticed stars twinkling? That is not something the star is doing. Instead, it is caused by our atmosphere. You see, shifting pockets of air causes the steady light from the stars to shiver or to twinkle. This places a limitation on pretty much all ground-based telescopes, something we have noticed ever since their creation. Astronomers have long pointed their telescopes at the sky, clamoring for the best possible glimpse of the stars above. And while technology has vastly improved, creating larger, more effective, more polished lenses and mirrors, Earth's atmosphere remained as a steadfast obstacle. This is also true for the advent of spectroscopy. We are able to learn so much more detail about an object by viewing it in the entire electromagnetic spectrum. Yet, as we mentioned earlier, a part of protecting us and keeping us alive means our atmosphere is blocking out things like UV light, ultraviolet, X-rays, gamma rays, and infrared radiation. Meaning from the ground, it is challenging at best to study any of these wavelengths. So, then what is the answer? Why not go up? Perhaps get over the problem, if you will. What if we were to put a telescope into space above the Earth's atmosphere? Perhaps this telescope could even orbit Earth, allowing it to stay up there observing for a long time. Well, this is exactly what we did with the Hubble Space Telescope. And for over 3 decades now, it has been helping us gather data, make observations, and study our universe in ways we could not accomplish before it. In fact, some might say it is the most productive scientific instrument ever built. Hubble was launched in 1990 by NASA. In the time since then, it has gathered more than 1 million observations. This wellspring of data has found its way into every astronomy textbook lining our shelves. It has helped scientists write more than 21,000 published scientific papers, authored by over 25,000 astronomers, and to this day is transmitting 150 gigabytes of data to Earth each week, which for technology from the 90s is very impressive to me, although it has had some upgrades since then. Before we get into some of the major discoveries we have made using Hubble, let's first turn our attention to the past. I would like to turn that attention towards the year 1946. Astrophysicist Lyman Spitzer wrote a paper called Astronomical Advantages of an Extraterrestrial Observatory. In this paper, he wrote about the advantages and benefits we would gain from having an observatory in space, one that sat above Earth's atmosphere. Then, about 20 years later, in 1966, NASA launched its first orbital astronomical observatory named OAO-1. This program would see a total of 4 observatories launched and would serve as a foundation for Hubble. In short, these were its predecessors. Fast forward just a couple of years, and we were planning the next steps beyond the OAO program. Spitzer was gathering the support of other astronomers for a large-scale orbital telescope along with addressing the concerns of its critics at the time. This would all come to a head in 1969 when the National Academy of Sciences gave its approval for the Large Space Telescope, or LST project. It was at this point that planning for what would become the Hubble Space Telescope truly began. At the same time as this, though, the funding for NASA space programs began to decline, which affected the program. Changes would be needed to make the telescope fit within budget constraints. Of the number of options discussed to achieve this, the one that got selected was a reduction in the size of the primary mirror, from 120 inches to 94 inches. It was suggested by NASA that the telescope have a lifetime of 15 years. This meant that the instruments would need to be interchangeable, so that replacements and servicing could be performed on the telescope even after it was launched. A balance was needed here between the cost of the instruments and their effectiveness for achieving science that was worthy of the project. It was decided that the telescope would be equipped with 3 types of instruments: cameras, spectrographs, and interferometers. We will cover more on these later in the video. For all the things that went into the telescope itself, planning, designing, deciding on its instruments, there was another problem that needed to be solved for this whole thing to work: a launch vehicle. After all, what good is a space telescope if we would not have been able to get it into space? NASA and the contractors it partnered with came up with a potential solution for this. They set out to develop a vehicle that could achieve orbit, return to Earth intact, and could be used repeatedly. With this, the concept of the space shuttle was born. The shuttle would be capable of deploying the LST into space and bringing it, or astronomers, back to Earth, if necessary in terms of the telescope. This also set parameters for the size the telescope needed to be. Its designers created it such that it would fit snugly inside of the shuttle's cargo bay. With all of this brought together, Congress approved the budget for the project in 1977, and thus began the building of one of the most sophisticated satellites ever constructed. After considering the options of servicing the telescope in space versus bringing it down to the ground for service, plans were made to conduct servicing missions with the telescope in orbit. Of the 2 options, this one was easier on the budget, and at the same time, with all the stuff that had come together, the project was given a new name, which is what we all know it as today, the Hubble Space Telescope, named after astronomer Edwin Hubble. And after hard work put in by every team on the project, Hubble was assembled and ready for launch by 1985. However, as is often the case with this sort of thing, the launch window did not go as planned. In 1986, a very sad and unfortunate disaster struck when Space Shuttle Challenger broke apart 73 seconds into its flight, killing all 7 crew members on board. This forced NASA to ground the Space Shuttle fleet for 2 years, which of course grounded Hubble with it. The team made the best of this time by making improvements to the telescope. Its solar panels were improved with new solar technology. The shroud at the end of the telescope that houses the science instruments was modified to make the replacement of them during servicing easier. And its computers and communication systems were upgraded. After this, the telescope was stress tested further to prepare it for the harsh conditions of liftoff and space. 4 years later, the fateful day arrived. On April 24, 1990, aboard the Space Shuttle Discovery, Hubble lifted off from Earth and began its journey. The next day, Hubble was released into orbit, ready to peer into the vast unknown of space, offering us first ever glimpses of distant and fascinating cosmic shores yet to be described. But Hubble was soon met with its own disaster. Upon returning science data to Earth, astronomers did not see the crisp, point-like images of stars they had anticipated. What they saw were stars surrounded by large, fuzzy halos of light. It was soon determined that the edges, just the edges, of the telescope's primary mirror had been ground too flat, by no more than a fraction of the width of a human hair. A fraction of the width of this right here. This happened due to a flaw introduced into the test equipment used to evaluate the mirror's curvature prior to launch. So while the mirror was perfectly smooth, it was not able to focus light into a single point. As we covered earlier, Hubble was designed with many replaceable components, but the primary mirror simply was not one of them. So this meant that another solution would be needed. And because the telescope had been designed such that it could be upgraded in orbit, engineers were able to come up with one. This came in the form of a set of nickel and quarter-sized mirrors that would remedy the effects of the primary mirror on Hubble's other instruments. Given the name the Corrective Optics Space Telescope Axial Replacement, or COSTAR for short, this refrigerator-sized device could deploy the corrective mirrors into the light paths of the telescope's other science instruments to then focus the images properly. With this, Hubble was officially up and running, and properly capable of performing science. But that was over 3 decades ago, so let us return to what instruments Hubble is performing science with today, starting with its cameras. At this time, Hubble has 2 primary cameras used for capturing the images we see from it today. One is called the Advanced Camera for Surveys, or ACS, and the other is called the Wide Field Camera 3, or WFC3. The ACS was installed on Hubble in 2002. It was designed primarily for wide field imagery in visible wavelengths, but it can also detect ultraviolet light and near-infrared light. ACS has 3 cameras called channels that capture different types of images. Due to an electronics failure in 2007, 2 of these science channels were rendered inoperable. However, during one of Hubble's 5 servicing missions, this one in 2009, these 2 channels were repaired. WFC3 was also installed during the same 2009 servicing mission. This camera provides wide field imagery in ultraviolet, visible, and infrared light. WFC3 was designed to complement ACS and expand the imaging capabilities of Hubble in general. So now, ACS can primarily handle visible light imaging, while WFC3 probes deeper into infrared and ultraviolet wavelengths. These together provide us with a more complete view of the cosmos. Hubble is also equipped with spectrographs. I have covered spectroscopy on my channel before, but to give a quick overview, it helps us study objects in the universe by breaking down light into its component parts, like a prism splitting light coming through the window. So, any object that absorbs or emits light can be studied with a spectrograph. At this time, Hubble utilizes several spectrographs, including the Cosmic Origin Spectrograph, COS, and the Space Telescope Imaging Spectrograph, STIS. These 2 complement each other nicely and can provide scientists with detailed spectral data for a variety of celestial objects. STIS is a versatile all-purpose spectrograph that handles bright objects well, whereas COS can measure exceedingly faint levels of ultraviolet light emanating from distant cosmic sources, such as remote galaxies and quasars. Going back to the cameras, WFC3 also has spectrographic capability and is often used in the study of exoplanet atmospheres. These, along with a couple more that serve as backups, provide a full set of spectroscopic tools for astrophysical research. This brings us to the final instrument set on Hubble, which are its interferometers. And they serve a dual purpose. They help the telescope maintain a steady aim and can also serve as a scientific instrument themselves. There are 3 of them aboard Hubble, and they are called the Fine Guidance Sensors. They measure the relative positions and brightness of stars. To give an example, when Hubble is pointing at a target, 2 of the 3 sensors are used to lock the telescope onto the target. For certain observations, the 3rd sensor can be used to gather scientific data about the target, such as angular diameter or position. With all 3 types of equipment aboard Hubble, it is able to perform a wide array of scientific study and data gathering that just far exceeds what we can achieve with ground-based telescopes alone. Of the observations Hubble has gained for us so far, there is one that, to me anyway, stands above the rest. This is known as the Hubble Deep Field, and the first one was taken in 1995. 1 year earlier, Robert Williams, director of the Space Telescope Science Institute in Baltimore, Maryland, became interested in Hubble's ability to observe distant objects. He had seen exposures taken in May and June by one of its cameras at the time, known as WFPC2. But what did he see in this data? What was revealed to him was a cosmic zoo of objects, suggesting that another deep exposure could reveal unknown parts of the universe. Williams had something known as Director's Discretionary Time, which gave him access to 10% of Hubble's observation time. He used some of it to take a long exposure of this patch of sky. Rather than having to wait for lengthy proposal and approval processes, these observations would be immediately available. They selected this spot to image because it had no nearby stars or objects, and it had no known galaxy clusters. He and the team he put together for this did not want any brighter objects to drown out the fainter ones that might have been visible there. For a quick size comparison, the patch of sky they selected was about the equivalent of holding a pinhead at arm's length up to the sky. What we saw there was far different than its apparent emptiness suggested, thus coming to be known as the Hubble Deep Field, and it opened up a whole new way of studying the more distant aspects of our universe, peering further back in time than we ever had before. As time passed, more deep fields would be taken by Hubble. Let's have a look now at some of the other awe-inspiring photos that Hubble has taken for us. For pretty much the entirety of my lifetime, Hubble has been helping us study, gather more data, and learn about our universe in ways that were simply not possible before its time. Part of what made this so achievable was the fact that it was designed to be serviced in space. This has allowed it to long outlast what it could have otherwise. I mean, think about it. It was originally slated or suggested for 15 years, yet here we are up to 34. As pieces of equipment failed, we were able to replace them with servicing missions. Even with this, though, as we all know, nothing lasts forever. And with the drag of Earth's atmosphere on the telescope, I expect it will fall back to us here on Earth somewhere in the mid-2030s, thus ending its long role in scientific discovery. This, of course, depends on whether or not we propel it back into its intended orbit, but that is left to be seen. Either way, let us appreciate all that Hubble has done for us up until now, and continue to look forward to the science it still has left to perform in its life. If you would like to learn more about spectroscopy, which is one of the techniques Hubble uses to study the universe, please consider checking out my video right here. And of course, I hope you all learned something today, and let's all step outside tonight and look towards the stars.